beginning of lecture number 14, and this is the end of chapter 8, 8.3 and 8.4, confidence intervals about proportions, also confidence intervals about the mean when the standard deviation is unknown, which introduces us to the t-distribution. All right, so we are going to go into estimation, also known as confidence intervals, and we've called that CI, confidence intervals. And once again, your book likes to review the three possible cases. They make a big deal out of it. But the point is, if you have the fact that in this case, sigma is not known, that's the biggest change in 8.3. And then you have to have one of two things happen. If you happen to have a small sample size, then you must have normally distributed situation, or case 2 would be if you already have normal, then you don't care what n is, and could be anything. And case 3, well, we don't want to talk about that because that is not covered in 262. That's the unfortunate case where you have a small sample and you don't know if you have normality, then you can't do anything about it in this particular class. So there's the review of that. Let's go with what's called the t-distribution, our second continuous distribution. It's very much like the z in a lot of ways, except you'll notice that the table is a little bit different. In fact, I plan to give you a better table than your book has, so I'll explain that later. The t-distribution is a specific kind of bell-shaped distribution. It has a lower height and greater spread, so it's a little bit flatter. Speaking of flattening the curve, the t-distribution is kind of flat, whereas the z-distribution, a little bit less flat. So z on top, t on the bottom, and they're similar yet different. Well, as the sample size becomes larger, the t basically becomes the standard normal known as z. So typically when you get around 100 or so, many times it used to be even 40 or above, they would just say let t becomes z, but they don't do that quite so much anymore with technology. Even the smallest differences between the two become more magnified. But we have this new idea called degrees of freedom. It's equal to df, degrees of freedom, and it's n minus 1. Very easy formula. You don't have to show your work here. And it helps us read the table and kind of determine which t curve do you have. They're all slightly different. This we're not going to spend a lot of time on, but your book likes to bring it up, and it certainly doesn't hurt. The mean of the t-distribution, like the z-distribution, is equal to 0, but the standard deviation happens to equal the square root of the df over df minus 2. We're not going to be using this. Don't worry about it. It's just sort of a side footnote. The book does talk a little bit about it. It's not uninteresting. It's just we don't have time to go into depth. And they have a little bit more explanation here, where if the standard deviation of a standard normal distribution is equal to 1, that of course is sigma, then the standard deviation of the t-distribution would be a little bit more, so it's more spread out. It's just more spread out, a little bit flatter at the top, a little bit more spread out at the tails. Wider tails. It continues staying above the horizon a little bit longer than z might. Although none of them ever go below the horizon, as you know. It's an asymptote. Well, here they've given us the number of degrees of freedom, 16. So df is equal to 16. That's given to you. And 0.05 area in the right tail of a t-distribution curve. Let's see if we have a picture that might put some light on this. So this table is built in this way. The area in the right tail under the t-distribution curve is given to be 5%. So a picture would be, we're focused on the upper 5%. And also, t has 16 degrees of freedom, so a very common notation, which you may feel free to use if you want, is t 16, 0.05. As long as you make yourself clear, there's no requirement for this, but I like it when students are clear. I like it when people show their work. We're not going to be doing any standard deviations, for example, on the final, but when I've been grading them, and I'm almost done, some people just assume that I can get the answer by a divine inspiration or something like that. No, I need to see the details. You get points for the details. When you give me the details, you get the points. Simple enough. Enough said on that. Most of you are doing that. Some of you are not. Okay, anyway, degrees of freedom 16. Area in the right tail 5%. Yes, that yields a magic t value of 1.746. Notice this has 3 decimals. Z often has 2, but you can use 3 in those couple of special cases if you wish. But t, on the other hand, the standard is 3 decimals. Most students don't seem to pay any attention to this. So when you do, I notice. Okay, anyway, that's the value as a picture. No big deal on the picture. And by the way, if we had exactly the same thing, but the 0.05, the 5% were in the left tail, the bottom 5%, all you'd have to do is put a minus sign on that. T and Z behave very similarly in that the values that are less than 0 are on the left, and the values that are greater than 0 are on the right, just like Z. And of course, when you have 0, you have the mean. Okay, now we have the confidence interval. It looks very, very similar to what we had before, except there's a couple of major changes. You might recall that with the Z distribution, the standard normal, we had a confidence interval of x bar plus or minus Z, or sometimes ZC, times sigma of the mean. Well, we don't have sigma anymore. If we did, we'd be using Z. Z and sigma are tied together. But when you have S, then you have to depend on the second choice, the t distribution. And yes, it's still going to be, this time, S over square root of n. So yeah, you could easily say x bar plus or minus t times S over square root of n. That's the way I do it by hand, but could be you need to calculate this separately for your calculator. When you use the TI, please show your steps. So many students are in a hurry to get done, don't want to show their steps, and yes, points will be lost if I can't figure out what you're doing. So even if you're using the calculator, which can be considered a benefit, all I ask is that you tell me how you got there. Is it second bars? Tell me that. We have a summary of some of the steps here at the end of this particular lesson. Well, the value of t is obtained by the t distribution for n minus 1 degrees of freedom. Usually n is given, by the way, and you have to subtract 1. Don't use your calculator. Do it in your head. Anyway, t times s is the margin of error. And yes, E is, of course, just equal to t times s sub x bar. And that could have been said as x bar plus or minus E in a very general way. Yeah, that part's exactly the same as before. So we just had to revise our estimates because the t distribution is not quite the same as z, and when you don't know what sigma is, s is considered to be a little bit more spread out. It's more variable. We don't really have the tight controls that we would over a sigma, so s is a second choice. And the t distribution did come about from Dr. Guinness, who had an enviable position. He had 2 big jobs. He was head of statistics at Oxford University and also the head brewmaster at Guinness Brewery. And his task, I guess, as he worked 2 jobs, was to take some beers home with him and experiment with them. And that actually created the t distribution. But because of certain, I guess, copyright laws or other legal matters, he had to call himself student. The student's t distribution. It's actually Gosset's t distribution, but that's neither here nor there. According to a survey released about 5 years ago, the total mean cost of employer-sponsored family health coverage was around $16,800, of which workers were paying an average of $48.23. So, anyway, a random sample of 25 workers in New York City who have all of this paid an average premium of $6,600 for family health insurance coverage with a standard deviation of 800. So there's a lot of numbers here. Make a 95% confidence interval for the current average premium paid by those in New York City. So you can ignore the first set of numbers and only use the second set of numbers here. And let's assume that it's normal. So we don't have to worry about 25 getting away. No, the normal 25 would be a bit of a problem, but we do have the word normal that basically saves us. Okay, well, sigma is not known. That's the way it is in this section, 8.3. But n is less than 30, which is not so great until we realize that, yes, normal is in play. So we would use the t-distribution to make a confidence interval for the mean. N is equal to 25. The average, the sample mean is 6,600, and the sample standard deviation, notice that's S. It came from a sample, not from something that's assumed. This is only $800, but it is S, and S leads directly to T, but if you happen to have sigma, it goes directly to Z, and this is something you have to be able to do on your own. So that's part of the skill of being in this class, is being able to read the instructions as you might do in the real world and make some sense of it. Is this sigma really sigma because it's well known? Or is it all from a sample? Just in context, and English skills do matter here. So if you can figure out, and if you think about it, it almost never is a problem, but some people just don't think, I guess, correctly, or don't know how to read English very well, or they're too nervous, or whatever it might be. But when you see it's all from a sample, that's S, and S goes straight to T. There are no exceptions here. S goes to T, and sigma goes to Z. So we're in 8.3 now. That's the key. So confidence level is 95% or 0.95, either way, but 0.95% is what's typically given. So S sub x bar is S over square root of n. 800 over square root of 25, that's 800 over 5. That's actually pretty easy, which is 160. So we see how it's kind of gotten a little smaller, kind of tightened the spread a little bit, because we're talking about this confidence interval for the mean based on the samples. So degrees of freedom is always equal to n minus 1, a very basic formula. 25 minus 1, of course, is 24. So that's it. When you use the table, or perhaps your calculator, don't use 25, use 24. Now, this part is kind of unnecessary, but this is how your book explains it, so I guess I will go ahead and explain it once. But the table I give you will avoid this kind of issue. So the area in each tail, which might not be given, in this particular case will be 0.5 minus 9.5 over 2, which is 0.5 divided by 0.470, and this would be 0.95 over 2, I guess. And so anyway, we get 2.5% in each tail because of the fact that it's a 95% confidence interval. 95 confidence interval means that we have 2.5% in each tail. We've seen a picture like this before. So if we have 95% in the center, we have 0.025 in each tail. And because it's a t-distribution, we're aiming at the right tail in most cases. So let's look for that positive value. We really have two different values. And the value of t in the right tail, depending on the table that you have, will be 2.064. And there's another one over here, which, I don't know, a little bit redundant, but it's there, minus 2.064. Those are our t values. Okay, so now we go ahead and use the formula. X bar kind of controls the confidence interval, just exactly like before. Start with 6,600. And then we're going to use the t value, something that does not repeat itself very often. It's a table value. They don't have the big three that repeat over and over like Z has the advantage of. And so that number will be multiplied by what we just calculated from the prior page, 160. So when you basically double the 160, you're up to 330. And so now it's just a matter of adding and subtracting. Use your calculator, round to the nearest penny, nearest cent, 2 decimal places. That's the way business math always works, unless they say otherwise. And we're not going to say otherwise, so we expect that you will remember to round to the nearest cent. Now the book once in a while goes to 3 decimals. That just seems to be a slight pain in the neck for me. Go ahead and give me the nearest penny, and everybody will be happy about that. So to recover what we just did, with 95% confidence, the current mean premium paid for family health insurance in New York City, who have the insurance coverage, is between $6,269.76 and $6,930.24. So that just repeats what we just did. And here's a picture I just drew. This probably could have been shown a little bit earlier, but there's the t values that come into play, and that's how we basically get the t value. But the calculation is done by algebra, perhaps calculator if you explain your step. Here's another example, 64, which of course is greater than 30. We don't need to worry about normality. These randomly selected adults who buy books for general reading were asked how much they usually spend on books per year. The sample produced a mean of 1450, standard deviation of 300. We'd like a 99% confidence interval here. So to kind of summarize what's going to happen here, if we have 99% in the middle, that means our 0.01, like P versus Q, will have to be divided by 2. We've glimpsed this before. That leaves us only 0.5% in each tail. And because the tables seem to be focused towards the right, we'll usually use this one for our t-value, which is the positive version of it. It's really both, but one will do because the plus and minus is already built into the formula after all. Okay, so we do have n greater than 30, even though sigma wasn't known. So t gets to be used because we still don't know sigma. And we want to get the confidence interval. So n is 64, x bar is 1450, S, not sigma, very important, is 300. So if you screw up t versus z, you're looking at less than half credit no matter how much work you showed. And I will try to give you a few points for kind of being in the right general zone, but it's not the same, and sometimes it makes a big difference. Often they look about the same, but for smaller n especially, it can make a big difference. So anyway, confidence level, so let's go ahead and get some calculations out of the way. There's S sub x bar, we divide by square root of n. On the regular S, we divide by 8, of course, and that's actually a nice exact number, $37.50. So, degrees of freedom is now 63. Your book goes a little deeper than most books do. They go all the way to like 75 or so degrees of freedom. When you find something that doesn't land on a table, then you go to the nearest one. So maybe if you have to pick 60 versus 70 on a different table, go ahead and use 60. Just pick the closest. I'll really do my best to avoid the ones that are halfway. Anyway, this part you will probably not need, but as we already glimpsed here, I'm not going to worry about this. You've got 0.5% in each tail. You could either do a quick sketch or just simply look at another heading, which we'll explain based on the other edition that I have. So we'll get to more of that later. The confidence interval formula is here, of course, looking very, very similar to the last section. And we'll have to take around 2.656 times 3750. Gives us a plus or minus just about exactly $100 here. Too bad it wasn't exactly $100, but it's essentially from about 1,350 to 1,549. And feel free to use other kinds of intervals. And I've got a cat here on my leg, so excuse me for a second. Good thing the camera's not on. But it's roughly 1,350 to 1,550. But once again, round to the nearest cent. That seems to be the accepted method, and that's what I always go by. And always list the smaller number first, bigger number second. You can use absolute algebraic identities, that is intervals. So 1350 and 40 cents, comma 1549, 60 if you'd rather do it that way, or you could do where mean is in between the two, and we just sort of fill those numbers in. So both of those are acceptable as well. But use the same level of accuracy. 2 decimals here is just right. Don't give me 1 decimal and then 6 decimals. That just looks a little bit out of kilter. All right, so this just summarizes what we just did. With 99% confidence, the mean will be in this range. It's kind of a wide range, but we'll only be wrong 1% of the time. So we lose some precision, but we gain a lot in accuracy. It's kind of a trade-off. So the 99 goes in that direction. So what happens if the sample size is too large? Well, some tables actually go on and go by the hundreds, 100, 200, 300. And once you get to about around 1,000, though, it's so close to Z that you may as well use Z. So even they will go ahead and do it. Now, if you have technology and you happen to crunch the numbers, it can be slightly different than the Z value. Okay, as long as you show your work, I'll believe you. You have to tell me how you're using the calculator. You just can't pick a number out of thin air and expect me to buy it. You have to tell me where it came from. I assume that you're using the table unless you show calculator steps. That's the general plan. So anyway, we assume you're using the table. That's what has been the pattern. Maybe 60% of people or so have been using the table, and maybe 30 to 40% are using a calculator. And if you're not using a TI, then you have to really explain yourself, because I probably don't have it, and I'm going to have to check it out. So anyway, use the t-value from the last row, which is basically approximately z. And that basically is the normal distribution as the approximation. And that's when you get a very large value, such as in the hundreds or thousands. We'll try to avoid doing that. So the t-distribution, we'll fill in a couple of things here. This is something our book didn't really go into detail on, but just like z is equal to x bar minus mu over sigma over square root of n, we could use the t-distribution in terms of s. That's the biggest difference, is s. I'll just circle that. And otherwise, it's all the same. And so if you happen to have less than 30, you better have normality. Or if you have greater than 30, then it doesn't matter as much. This version uses t sub c. I do not care if you use that or not. It doesn't hurt at all. So here's some properties, very similar to the z. Mean, median, mode are supposed to equal 0. We don't pay that much attention to that. Still bell-shaped, still symmetric, a little bit flatter, a little bit wider. Still the total area, the total probability is 1. The tails are thicker. Yeah, it takes a little while. Whereas z rarely goes beyond like 3.5 in either direction. T can go to 4 or 5 a lot of the time. Standard deviation varies with the sample size, but it is greater than 1, and our other book decided to give us a formula. We were not very interested in that. And the t-distribution is actually a family of curves, several curves kind of superimposed on each other, distinguished by the degrees of freedom. We don't go into a lot of details on that, but the story goes with that if you had a quiz with 10 people taking it and you only had 9 of the scores, but you did have the average, you could back into the 10th score by just looking at the total points minus the 9 that you know about, and the 10th would show up kind of by default. So that 10th one does not have any freedom. The first 9 are the ones that are free, so to speak. And that's as far as we need to go, because we don't need to go into an advanced statistics lecture of a few hours. We don't need to bother with that. Anyway, for all we need to know, df is n minus 1. Good enough. Most of the time, n is given, so you have to subtract 1 yourself. Okay, there we go. So yes, we already said that. And picture, say df is 5, df is 2. You can sort of see how they're going. df equals 2 is rather an extreme case. It's rather a very flat curve up here, and it's very thick going out that way and along that way. 5 is being a little bit more moderate, but certainly the deep blue standard normal curve is the kind of the master curve. That's the one that we seem to use the most, but t does come along in certain cases, especially if you don't know sigma, which the current way of thinking is that sigma is often unknown, so t has become much more popular than when I first started teaching statistics. I've seen procedures change in the time that I've been teaching stats. So we'd like to find the critical value t for a 95% confidence interval. This just asks us to use the table. Sample size is 15. Notice that's n. So we have to calculate n minus 1. Not very difficult. We get 14, amazingly enough, and kind of a review, but notice how this table has changed. We can notice the level of confidence. That seems to take some of the pressure off. It says 95% is a pretty popular one. We don't have to worry about the 0.025 that we did before. I mean, it's there, and you can back into it and use it with the curve that we just drew and all that. And by the way, they've got either measured in one tail or two tails, because when it comes to hypothesis testing, chapters 9 and 10, we will focus on how many tails there are. Sometimes there's 1, sometimes there's 2, but that's coming up later. Anyway, just like before, we got a t-value of 2.145. That's the positive version. And yes, we have a negative version as well if you need it. Now, they're always going to give you the absolute value of what they're after. So the table is reading a right tail value. If you need a left tail, stick a minus sign on. If you need a two tail, put both plus and minus on. And for these confidence intervals, well, basically you've got the two tails. So you've got the plus and minus built into the formula, so you have even less to worry about here. So this is an easier table. This is the one I choose to give you, so take advantage of it. Unless you're just using a calculator, a TI type of thing, and then you just have to know the procedures for that. Anyway, DF was 14 and C is 0.95, 95%. And let's continue. So we found that T was equal to 2.145, which really stands for plus and minus 2.145, two different values there. And yes, C is that value in t is 2.145. That's just a review of what we just did. But we had to get the 14, not the 15, as the other number. And yeah, you could find the TC with a TI-84. And you need to know what area under the curve is to the left. Very important, to the left of T. That's just the way they decided to do it. So we're going to have to basically add the 95%. I think a sketch is warranted here. 95% in the middle. And then the extra 0.025 over here. So if we're looking at a value here where I put the star, together these values make a 0.975, and that's what you'd have to type into the calculator. So just because you have a calculator doesn't mean it's going to do all your thinking for you. Some people think it does. But notice how we have the two numbers after inverse t, when you get there, is area left and df. So that could go in your notes maybe, or just your memory block if you are using ATI, which we encourage you to do. So 95% of the area under the curve lies between t equals plus n minus 2.145. And yes, now we're back to the area in the middle, the 95%, but the table, that is the calculator, wants to go to the left. The table wants to go to the right. So be sure you're clear on the difference if you are a TI-84 user. Okay, here's a confidence interval for a population mean. And let's see, we've got 1 of 2. Oh, we don't need that. But sigma is unknown. So I lowered all these titles, and they're still being cut off by the black. Anyway, whatever. So sigma is not known. The sample is random. Population is normally distributed. Or n is greater than 30. We've gone through that many, many times. And we can find the sample statistics. Here, x bar is equal to the sum of the x's over n, which is just basic statistics, and s is equal to the sum of the x minus x bars squared divided by n minus 1. So these are just review of prior formulas that you may need to use, but my habit is to go ahead and give you these values. We're not going to have you reinvent the wheel on these problems. We just want to get you to the heart of the matter. So identify the degrees of freedom. This is the easiest part of all. It's simply n minus 1. And use whatever table you may have. This probably does not affect you. Find the margin of error. E is equal to the t times s over square root of n. That goes directly to the matter algebraically. Find the left and right endpoints. Form the confidence interval. Of course, to go to the left, you must subtract the margin of error. Go to the right, you add the margin of error. So the interval is in between x bar minus e and x bar plus e. And yes, you can put the mean in between those two values, or use algebraic notation, or just simply use the two numbers with the word TO in between. You choose. Pick any one of those three. Now we're going to select 16, only 16 coffee shops, and measure the temperature of the coffee sold at each. The sample mean temperature is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold. And here's the thing, it does say normal, so 16 is okay. If it didn't say that, you'd have to shut it down. And that's not going to happen on a test. Might happen on web work, might even happen on the written homework, but I'm not completely sure about that. Now, because sigma is unknown, which is the case in 8.3, sample is random. Temperatures are approximately normally distributed using the t-distribution. So if n is 16, of course df is 15. That's kind of easy. X bar is equal to 162, S is equal to 10, C is the 95% interval, and by the table, maybe even the calculator, you could find the t value as being 2.131. So the margin of error at the 95% confidence interval is basically TS over square root of n. We found the t. You should check that and make sure you know how to do that. And you multiply by the s over root n, and you get approximately 5.3. I would have gone to a couple of decimal places on this one. This edition doesn't seem to like that, but please use more decimals than this if you want more accuracy. It could actually matter on your points too if it's considerably poor, but I'll try to do the best I can. by giving you as much partial credit as I possibly can do that. Confidence intervals require left endpoint and right endpoint. So x bar minus e is very easy to do. You just subtract the 5.3. The right endpoint says that we add the e, and of course we get 167.3. So our two numbers are there. And we even have a number line. How about that? This is not required. So with 95% confidence, you can say the mean temperature of coffee sold is between 156.7 and 167.3 degrees Fahrenheit. Next example, we pick 36 cars. That number is bigger than 30. We're okay with the normality part. They're the same model that are sold at a car dealership that determine the number of days each car sat on a dealership's lot before it was sold. That's something I hadn't really thought about before, but when you buy a car, whether it's used or new, it probably has been sitting there for at least a day, maybe even a lot longer than that. Might be interesting to know that, but I'm not sure if you can find that out. But anyway, here, a lot of turnover here. It's less than 10 days for the sample mean. And the sample, so they're handing that one to you, so that's very nice of them to do that. Sometimes you have to dig for that a little bit, but that's clearly S. We'd like to get a 99% confidence interval for the mean, population mean number of days that the car model sits on the dealership's lot. And sigma is unknown. The sample is random, n equals 36, yep, greater than 30 like we said. So when n is 36 and x bar is given to be 9.75, the number of days, average number of days almost 10. Standard deviation, they already calculated it for you, it's 2.39, and yes, we have a 99% confidence interval. And obviously df is 35. You can subtract 1 in your head and use whatever table it is or calculator to find the value of t to be 2.724. That's also known as t with 35 degrees of freedom and a 99% confidence interval. Well, the margin of error, which is a nice way to go, is to take ts over square root of n. There they are. Those are the numbers that yield eventually a 1.09. Not very large margin of error, considering we have a sample size of 36. So here's how we build a confidence interval. Left endpoint, right endpoint, we subtract the margin of error. 9.75 minus 1.09, it's around 8.66. And of course the high side endpoint is the same thing except we add. So now we have our answer, which I just choose to write the algebraic style, and that seems to be a little faster. And there's a number line too. How about that? We do not need that. So here's a kind of a nice flow chart, and we can find out whether we need to use normal or t-distribution or maybe even none of the above. So the big question is the population normally distributed or n greater than or equal to 30? And if it is neither one, you just shut it down. This is not in this class, except perhaps on web work, maybe briefly on the homework. So then the big question is sigma known? And if it is, you're in 8.2, and that's the z distribution that we're more familiar with, and so the margin of error is z sigma over square root of n. But if it's not, then we're in 8.3, and then you must use t because sigma is unknown, which means of course that s is known. And so we have to use S, and then we have to use T. It's just a chain of events that never, ever changes. So once you get the hang of it, it's really pretty obvious. So do you have known sigma or not? And you have to read to see if sigma that you do have, or S that you do have, came from a sample. And then you put a label on it, and then you go right to the distribution. And it should be clear if you just read the problem. So if you use the t-distribution, it's basically the same thing, except now it's ts instead of z sigma. And yes, of course, we have the degrees of freedom. So here, all we're going to do is see which distribution we're going to need. And here we only have 25 newly constructed houses. So I'm looking for the word normal. There it is. So I just went ahead and took care of that right away. Sample mean construction costs 181,000, and the population standard deviation is 28,000. Okay, so should we use the normal, the t, or neither to construct a 95% confidence interval, which by the way has nothing to do with it, for the population mean construction cost? Explain your reasoning. We do have normal. That's good to know. So that might mean that, is it normal or greater than 30? Well, no, not that one, but yes, that one. And so, yes, of course the answer is yes, the population is normally distributed. So even though that n equaled 25, which is less than 30, we could still use whichever distribution because we have normality. So we're in the game, we just don't know what game we're playing. Of course, then the next question is sigma known? So we read the question very carefully, and yes, it is. Notice how they did say, if we go back here, that the population standard deviation, they didn't even try to hide it here. They just gave it to you on a silver platter. And not all problems will do that. But sigma is known, so yes, because it is, we'll use the standard normal, or if you prefer, z distribution from 8.2. Now we'll go into 8.4. So if you'd like to take a break, now's a good time. We kind of changed the subject, going to proportion. But the good news is we can stay with z, proportion, provided we fulfill some pretty basic requirements. Gets us back to the z distribution, which undoubtedly you're more familiar with. So the value of the standard deviation with regards to the population, the sample population proportion is what I'm trying to say, which gives us a point estimate of S sub p, or actually sigma sub p to be completely accurate, is calculated as follows. Here, S is estimating sigma. P happens to be involved. So what we'll do is we'll use the formula square root of p hat q hat over n. We don't have p, or we'd use it, but we don't have it, so we have to use p hat and q hat. So subtle distinction there. And now the confidence interval is done just a little bit differently. It still has a margin of error. It still has your mean, so to speak, p hat, plus or minus an error, which we'll get to in a second. The 1 minus alpha also kind of relates the alpha to the kind of confidence interval. So let's go ahead and list them together. If you have a 90% CI, alpha is equal to 0.10. That's the stuff on the rejection region where you're not confident, and traditionally it's expressed in a decimal. 95% leads alpha to become 0.05, and then the 99% means alpha becomes 0.01. And sometimes you have to divide the alpha by 2 in certain cases. Okay, so we have z from the standard normal distribution. This last part here is the margin of error, so I'll put the e right above it. And that's just another style. It's saying almost the same thing as before. It just looks a little bit different, but at least we get to go back to z again. Okay, so this example says that there's a sample of 1,821. That's just slightly bigger than 30. And we're talking proportions now. 75% of the people, including this study, said that having basic needs met is very or extremely important in their vision of the American dream. So p hat here is equal to 0.75. Q hat's pretty easy as well. 1 minus 0.75 is 0.25. So what's the point estimate of the population proportion? Well, we have our p hat. And of the population proportion p hat is trying to estimate the p, and that's going to be our 0.75. That's our best guess. That's all we have. We may as well use it. Now, it could be that the real p is 0.76 or 0.78. Don't know. But this is all we have so far. So I don't generally worry about A. That's kind of routine. But B is the one we're after. The 99% confidence level, the formula we just gave you. Find the percentage of all American adults who say exactly what we just did. Having basic needs met is very important, extremely important in their vision of the American dream. Very general platitudes, in my opinion, but let's get more specific with the math. Okay, so getting to the nuts and bolts and filling in some details that they got rid of. N is very large, 1821. The sample proportion is 75%, and of course, the sample proportion of failure, where they disagree with this statement, is 25%. And no, you don't have to show the work. The standard deviation, standard error, I guess you could say, the special formula we just gave you, which could be in your notes, is equal to the p hat, q hat multiplied together and divided by n. Sometimes these numbers get to be very small. And of course, when you square root a number that's less than 1, it actually grows to approach 1 from the other direction. And yes, np hat and nq hat are both greater than 5. This is a technical requirement. I've never made a big deal of it because every problem I give you has that happening. Now in the homework, we may have sought out a few that weren't just to show you that it doesn't always work that way. And if one of them fell below the 5, then you'd have to call the statistician because it's beyond the scope of basic statistics, but that's not going to happen on a test. So the point estimate of P, of course, is P hat equals 0.75. It's kind of easy. But the confidence level is 99%, and we go back to what we already learned, and I'm going to use the 2-decimal version of the 99% Z value. So that's good. So P plus or minus Z times S is equal to 2.58, that special value that we've seen a few times before, so we just keep on using it, and plus or minus what works out to be 0.01 times 0.75, and actually that's going to be Z times, yeah, okay, I got that wrong. So 0.75 is what P is. Now my pen battery is dying, so I got to make through this. Try the other pen. And we got 0.75 plus or minus 2.58, that's the Z value. This is going to be multiplied by the standard error, that is SP hat. So we get eventually 0.75 plus or minus 0.026. That's around 2.5%, by the way. Very easy to add and subtract that. And going an extra decimal, a third decimal, is very typical. So we hope you'll do that and give us a little bit more accuracy. So there's a couple ways of expressing it. You may express it in decimal form if you wish, or you may go to more conversational percentage style. I'll let you decide about that. But the extra calculations here, which seem a bit redundant, are the margin of error, which is E, would equal the Z value times S. And so we just went through this, but that's where the 0.026 comes from. They kind of repeated themselves. Okay, another example. According to a Gallup study, college and college graduates conducted a few years ago, 63% of college graduates polled said they had at least one college professor who made them feel excited about learning. Wow, that's surprising to me because that means maybe 37% never had a professor that made them feel excited about learning. Now, I'm not going to say that I'm the one that does that to you. I hope I am, but to have 37% of college graduates who never had a teacher inspire them, wow, gosh, I hope, well, that's enough said about that. Anyway, suppose this study was based on a random sample of 2,000 college graduates. Strangely, though, they go for something that I would never do on a test, a 97% confidence interval for the confidence level here for P. Okay, so confidence level, 0.97. Well, we'll get to that in a minute. S will be P hat Q hat over N square rooted. So multiply P hat, which is 63%, and then the 37%, of course, was 1 minus P. Very easy calculation. And that does work out to be another very small number. However, Z is not so routine anymore. Here's the plan. You shouldn't have to do this on the test, but maybe on the homework, especially web work, you may have to do that. If 97% is in the center, that leaves 3% that has to be shared amongst two different tails. 0.015 over here, 0.015 over there. I'll put an extra 0 in, and since we're back to Z, the left tail is actually the easiest one, and you will find just by routine management of your normal curve table or even your calculator, you get closest to minus 2.17, and by symmetry, the other one is positive 2.17. And because this is being plus or minus anyway, we do not care if you put in the minus or the plus. I'll just put them both in and be neutral about it. They've chosen to go this way. I don't think I would go in this direction. I think that that's sort of misleading. I think that's based on the one-page table that was the Stone Age way of teaching this. We're up to the Dark Ages now. We're not in the Stone Ages, at least. Okay, anyway, we're at P hat plus or minus ZS. And the numbers we just got are plugged in. Seems a bit ironic that Z only gets 2 decimals here and gets 8 decimals over here. Well, the point is, the more decimals you put down, the better. And I know sometimes we encourage you to use z to 2 decimals because that's how we have a book. We have a book that uses 2 decimals, so I'm just trying to be consistent. I do give you permission to use the 3 decimals if you wish, but otherwise I would have like 100 different grading keys. It's already going to take forever to grade these finals, so please try to use 2 decimals for z, maybe 3. That would be the best way for me to handle it. And then the s, put as many decimals as you can stand. If you're not putting down 4 or 5 decimals, you're probably missing the boat. And I know it sounds a little bit inconsistent, but if you're only putting down 1 or 2 decimals over here, that's just not going to work. So give me a little bit more accuracy here. So it gets something at least very close to 0.023, 2.3%, and we see our answers that are very easy to get by adding and subtracting. So strangely used 97% confidence that of all the proportion of the college graduates who say that at least one professor made them feel excited about learning. And boy, I'm hoping you've had at least a dozen or so that have made you feel at least somewhat excited about learning in your major at least. And so it'll be between these two numbers. And we've got a pretty tight margin of error here. So that certainly helps narrow things down. But we'll keep it as 90, 95, and 99. The big three is all I care about. We have another sample size calculation. And for the estimation of proportion, kind of has two different versions. But here's the difference between this and the prior section in Chapter 8. As I sip my lemonade, given the confidence level, which you have to have given, and values of p hat and q hat, find a sample size that determines a predetermined maximum error. Margin of error, looks like a misprint here, so the margin of error, I'll just say E for now. Confidence interval estimate of P gives us N. And so I guess when you're determining which N formula to use, do you see a proportion anywhere? If you do, this is the one for you. And if you don't, use the other one. Some people, I guess, just don't know what proportions are. So ask yourself, do I see a proportion here? And if you do, oh, you're in this section, 8.4. If you don't, you're back 8.2. 8.3 does not have one. Now we have a couple of subtopics. If we do not know what p hat and q hat are, we turn it into a coin flip. 50-50, 0.5, 0.5. This turns out to maximize the n. Some books actually go into details, kind of a upside down parabola, which hits the maximum number of n at 0.5 for p, which of course means q is 0.5 as well. And if p is like 0.9 or 0.1, then we get values that are not nearly as high for n. N becomes quite a bit lower. We'll show you a dramatic example coming up later. Now, if you don't have any kind of estimate, you use 50-50. But if a sample is available, which would be clearly stated, you're not going to have to go out and get one, then you go ahead and put those numbers in and see what happens. It'll bring the numbers down from 50-50, guaranteed. Okay, so here's an example. This electronics company just installed a new machine that makes a part that's used in clocks. The company wants to estimate the proportion of these parts produced by this machine that are defective. And we have a within number, 0.02. That's the E. Within is always E. So we have E is 0.02. And we have a 95% confidence interval. We do have proportions. And we're just going to go ahead and use Z equals the very, very popular 1.96. If you've memorized any of the numbers at all, that's the one to memorize. That's the one we see over and over again, even at the late date in this class. What's the most conservative estimate of the sample size that would limit the maximum error to be within 0.02 of the population proportion? So when they say most conservative, it has nothing to do with politics. It has to do with math, and it has to do with the 50-50 deal. That's going to maximize the N, so it means that P and Q are 0.5, or P hat, Q hat if you wish. And so we have P hat, 0.5, Q hat, 0.5, and now we use the formula. Notice these are not squared, but you could do Z over E and then square it. That's what I often do, and then attach your P hat, Q hat. Whether you have the values or not, if you have them, put them in, and if you don't, use 50-50. Some books even say 0.25, which is 0.5 times 0.5, but that's up to you. Anyway, this is a rare one. We got exactly 2401. That's a big number, not great news, but this one did not involve any rounding. I think I mentioned before this doesn't happen often, but I guess I forgot that they had an exact example in here. It does happen, especially with a 95% confidence level. That's a nice even number. It sometimes goes through without any rounding, so don't call it 2402. We do not have to add 1 here. Okay, now we're going to change it up just a little bit, and a preliminary estimate says that only 7% are defective. So now p hat is not 0.50. It is equal to 0.07, and that's going to make a big difference. It bends the curve over towards where we don't need nearly as many n's to sample. And everything else is the same. E is still 0.02. Z is still 1.96. That corresponds to the 95% confidence interval. And let's see how things change. So P is down to 0.07 as we mentioned before, and Q, very easy to find. 1 minus 0.07 is 0.93. And you might think, oh, that number's bigger, but it's the 0.07 that matters. So make sure you multiplied all those numbers together, and then you get, there's an extra step there. And now we're to only 625.22. Yes, we do round up to 626, but compare versus 2401. It's about a fourth. That's a big savings. So in other words, get that sample. Your boss will love you for it. So if you don't have a sample, you're going to perhaps pay a mighty big price, to the point where you might not be able to get the job done because of limited budgets, etc., or limited time frames. So something to think about. Get that sample. Of course, if it's an invalid sample, it is garbage in, garbage out, but that's another story completely. Now we have a bit of a review of the TI-84. So these are all found in the back of the chapter. If you would like to take a longer look, there they are. We did this one in the prior lecture, so we had some things to do, and there we got an interval, Z interval. I think that was from earlier, 8.2. T interval from 8.3. Yeah, we had an X bar, we had an S sub X and N, and we had T available. Notice they type in N here, but we went ahead and did that, and this is sort of a prompt thing, so just go ahead and fill in the blanks on your test and just tell me how you got it. And so we actually do get those values there. I'm not going to spend a lot of time reviewing this. And this is 8.4, and this is the one that we kind of just did. Well, actually we didn't do this one, but we did show an interval, and here's, they're breaking the rule that I have. Here we are at 3 decimals, and here we have 5. That's a no-no. So I would just call this 0.776 and make them the same level of accuracy. So anyway, that's beside the point. Sometimes you may find that some few problems could be done from the 8.4 section by way of 8.2, and as long as it works and you show me the work, I will buy it. But not all of them work that way. You have to read them very carefully. If you see a proportion, you should, as a general rule of thumb, use the proportion, because you know that'll work, and you're kind of walking a tightrope if you try to apply 8.2 to 8.4, because sometimes it works, then sometimes it doesn't. So a few more examples here in this longer lecture. The population proportion, of course, as from the binomial theorem, we had the probability of success in a single trial of a binomial experiment is P. And yes, P hat, the sample version of that, is just X over N, and that's a sample proportion, as you can see yourself. X is the number of successes in the sample, and N is the sample size. Sometimes they ask you to figure that out. We haven't done that in a little while. And so the point estimate of the proportion of failures is Q hat equals 1 minus P hat. I'm so glad both the references I have use this, because when you have to drag 1 minus P or 1 minus P hat or 1 minus P bar or whatever around, it just makes the formulas much more tedious. You have no idea how tedious it can get. So it's amazing that some books still do it the old-fashioned way. But we have P hat and Q hat, as we just see there. And here is another example. In a survey of 1,550 U.S. adults, 1,054 said they use Facebook. Find a point estimate for the proportion of adults, proportion from population, that is, that use Facebook. So all you have to do is just divide X over N. X is clearly 1,054, N is clearly 1,550. So that looks like around 2/3. And so here we go. X is 1,054. P hat is X over N. And yes, you may express it either way. I'd go for a third decimal here, but roughly 68% is what we have. It's probably higher now. Confidence interval. So I'll fill in a few details here. This version uses a C confidence interval. Just think of this as being 90, 95, 99%. C is just sort of a filler for that. So the actual P that does not have a hat on it, that's the golden one, is between the lesser important P hat, subtracting the margin of error, and it's in between that and the P hat plus the margin of error, where E, the margin of error, is equal to C, Z, sub C if you wish, times the square root of P hat Q hat over N. And this is assuming that the estimation process is repeated a large number of times. And it is, so we're not going to worry about that. So here's the process. Identify the sample statistics N and X. Find the point estimate P hat. Simply divide the two, unless it's already given to you. Sometimes this is already given to you. Verify the sampling distribution of P hat can be approximated by the normal distribution. As we saw in another section, NP, this time NP hat, must be greater than 5, NQ hat greater than 5. Sometimes people skip this step, and as long as you're doing the rest of it flawlessly, I'm not going to say anything. If, however, you show the step and do make a small mistake, I figure they kind of cancel out a little bit. So those of you who are fastidious enough to remember this and show it to me, kind of buy back a possible small mistake and a little bit of extra credit indirectly, I suppose. So that's how I'm going to handle that, but I always guarantee you that none of these will be shut down. Find the critical value of Z, and this will be the big three, the 1.96, the 1.65, the 2.58. Those will be the only ones that we use. And find the margin of error. Of course, margin of error is equal to Z times the standard error there. Find the left and right endpoints and form the confidence interval. So yes, subtract to get the left, add to get the right. I'm not sure why this got to be backwards, but it did. And P hat minus E is the low side. P hat plus E is the high side part of the confidence interval. Okay, so using data, find a 95 confidence interval for the population proportion of U.S. adults who use Facebook. So P hat was 68%. So Q, of course, Q hat will equal 1 minus 0.68 or 32%. And N is 1550, that was given. Verify that we can go ahead and use it. Usually we're not even close to having a problem with this, but we would have N equal 1550, P hat equaling 0.68, so we'll multiply by 0.68 to get our 1054, and of course that's greater than 5. What I typically do is I go for the smaller one, and if that one makes it, then the other one has to make it. You can just quickly note that and save just a little time perhaps. So doing NQ hat first might be just a little bit more efficient, because then you got your 496. Of course that's greater than 5, and then P hat is greater than Q hat, case closed. Okay, so with 95%, we have the automatic, very popular 1.96, approximately 2, but please use 1.96. And the margin of error will be equal to that 1.96 multiplied by those P hats and Q hats multiplied together, divided by N, square root that part of it, not the 1.96 part, and we do get a margin of error of 0.023, roughly 2.3%. Margin of errors are always reported in reputable media polls, and this is a pretty good one. Usually if you get about 4 or so, that's pretty good. When it gets to 6 or 7%, that's not so good. If your margin of error is really low, sometimes it looks quite suspicious. And if they don't even bother to report it, then it's very suspicious. That's my opinion on the matter, especially in political polls or any other type of polls you might happen to come across. So to calculate these things, you take your P hat, subtract, so put a few decimal points in, subtract the margin of error, and you get the lowest number that's believable, 65.7%. And the highest number that's believable is found by adding the margin of error. This should be routine by now. That's why I'm going a little faster through it. Now we're up to 70.3%. So P, the actual P, notice no hat here, They can be deceptive because they look almost the same. I'll put that decimal in there. So P without a hat, the actual proportion is supposed to be in this range with 95% confidence. 5% chance it will not land in there, however. Okay, here's another example. Figure below is a survey of 800 adults, 18 to 29. We'd like to find a 99% confidence interval for the proportion of those people who get their news on TV. There are 4 choices. Do these add up to 100%? I believe they are close to it. With me, I kind of use all 4 of them myself, but that's neither here nor there. So we found what they were asking for was television. So the active number is 27%, so we'll go ahead and use that one. The others will be ignored. So P hat will be 0.27. Q hat is 1 minus that, which is 73%. And of course is 800, and they're going to verify that NP hat and NQ hat clear the bar. And yeah, P hat is smaller, so it's good they started with that. And yeah, we got 216. And then just to be sure, they check the other one and find that that's even larger. They're both greater than 5. So we're good. Yes, it is approximately normal, and we are fine. Z is in control. So they've picked the 3 decimal version of the 99% confidence interval, and that's perfectly okay. You may use 2.58 if you wish. If you're using something else, you must indicate what you did. So we don't encourage that, actually. So, yeah, that's my cat meowing at me. And you probably heard her there. So, yeah, you can't teach this. You're not smart enough to teach it. Sorry. She'll teach about catnip and cat food. Get down. Okay, anyway, sorry about the distraction. Our margin of error is 4%. Looks like exactly 4% to that level of accuracy. As you multiply it out and use your calculator. And so we find the left and right endpoints. This part is becoming quite routine. Hopefully everybody will just breeze right through this. And so we'll take 0.27 minus the 4% to get to 23%. And then we'll add that number. There's too many decimals here, in my opinion. We'll add the 4% and get to 31%. So P by itself, no hats, is between 23% and 31%. There it is on a number line even. And here we have a little bit more accuracy based on the TI-84 Plus. Now, they didn't go through the steps, but as you go ahead and do that, you would find that here we have 5 decimals of accuracy in our situation. So they had P hat as 0.27 and as 800, and follow the steps to get that if you're using the TI-84. So with 99% confidence, we can say the population proportion of those people who get their news on TV is between the 23 and 31%. And just as we did before, we can solve for n by using the P hat, Q hat, and Z over E squared. This book is deciding to more correctly take Z over E and square it. That's what I would do. A little bit faster. And P hat and Q hat may or may not be known, so you have to look carefully to see if it's known. And of course, we always round up unless it happened to be a whole number, which is rare. Don't count on that happening. The formula assumes that you have an estimate for P hat or Q hat. And if you don't, then it's the 50-50 coin flip, which is the worst case scenario as far as surveying. Unless you just like to go out and survey a little extra, then I guess it's not so bad then. If you have an unlimited budget and unlimited time, then sure, why not? Well, this time you're running a political campaign. It is, I guess, election year, and we wish to estimate with 95% confidence the proportion of voters who will vote for your candidate, and your estimate must be accurate within 3% of the population. Find the minimum sample size, that's n, needed when no preliminary estimate is available. And of course, that's code for the 50-50. And let's take a look. When we don't have the preliminary estimate, basically it's just, as we said before, now both my pens are dying battery-wise. You've got 0.5 for both. And yes, with 95%, we have the 1.96. And here's our within number. And notice we have to convert this to a proportion. Don't use 3, use 0.03. I remember making that mistake a few times as a student myself. Okay, let's continue. So n would equal the formula there, which is 0.5 squared. And we eventually would get 1,067.11, but that gets rounded up, and that means we have 1,068. Minimum sample size for this kind of accuracy. We've got a 95% level. We've got to be within 3% margin of error wise. That means you're talking more than 1,000 voters. Okay, now we're going to change it up a little bit. It's basically the same example, except now we have a preliminary estimate. And unless your estimate happened to be exactly 50-50, which I guess is possible but not likely, you're going to get a savings here as far as the n goes. It's going to be less than 1,000 something. So because p hat is 31%, q hat is 1 minus p hat. No, you don't have to show your work on this. And we're down to 69% that do not favor your candidate. So z is still 1.96, e is still 0.03. That did not change. And of course we have our formula, so I fill in some details. And okay, we get 913.02, and a lot of people might say that, oh, that's close to 913. No, it's closer to 914. And yes, we pay attention to that. Believe it or not, we actually do pay attention to the small stuff. So the minimum sample size has to be at least 914. That's still less than 1,068. So we didn't save as much as before, but at least we saved something, 150 or so less people to survey. And yes, of course, you'd have to go to 1,068 if we didn't have that prior estimate. So that'll about do it for today. Study hard. We're done with Chapter 8. We're down to only one major topic, Chapter 9 and 10. Really the same topic, hypothesis testing. 10 just continues 9, and we'll do a little hopscotch through Chapter 10, hitting the 3 most important sections. And we'll, in the last lecture, have a final review for you, and I'll have some more hints. And of course, when you show your work, you do get rewarded, so that's the bottom line.